Hello! In this video, I will show you how to use Bosch Rexroth ctrlX core control to communicate with CANBUS devices. We'll read CANBUS messages from Lithionics Never Die battery management system. We used this system before, and at that time, Bosch Rexroth XM22 control with dedicated module was reading CANBUS messages. There is a video available on YouTube under Bosch Rexroth Electric Drives and Control Product Support named CANBUS Message Processing with the PLC Intracontrol XM. In this video, I am showing how to pick and separate Lithionics messages from CANBUS telegrams, and later we'll use the same method. ctrlX core does not have dedicated CANBUS module, so we'll use CANBUS to serial converter and send data directly to its USB port. We'll use CANDUPTER by Avert Energy Systems. First, installation. CANBUS is connected using 9-pin D-shell plug as presented in this diagram, and depending on your network, you might need to add a terminating resistor to your plug. USB cable is connected to USB-C port in ctrlX core control. To verify if your adapter and CANBUS device work properly, you can connect this USB plug into your laptop and then use CANDUPTER utility suite provided at www.candupter.com. So, when we click on Diagnostic utility, we can search and detect our adapter, and after finding our device, we can run CANDUPTER Analyzer. Next, we need to set a proper baud rate for our transmission, and in our case it is 250 kilobaud per second. And then, when we click Start, we can see our battery management messages flowing, and we are ready for the next step and read those over the serial port into ctrlX core control. To program ctrlX core, we'll use latest version of ctrlX Works software. It will automatically find our control, and from here we can connect and log in into it. I will be using Node-RED app installed on our ctrlX core. We have some video and documentation, which I link in a description, covering installation and licensing of Node-RED, and videos showing basics of programming Node-RED. So, in this demonstration, I'll focus mainly on serial communication. Here's our flow, and first we'll add and configure Serial Communication Out node. We can simply drag it into our flow. Please note, system automatically shows a description of this node, and when we click on it, editor opens up, and here we can add new serial port. So, designation of this port for ctrlX core is /dev/tty USB 0. Character added to output messages is \n, and character for input split is \r. All other settings stay at default values except baud rate. Here we can pick it from the list or type it ourselves. And in our case, for BMS, system baud rate must be set to 250 kilobaud. So, we are done with the first node. Next, we'll add second node, but this time it will be serial in node. and we'll assign it to the same serial port. We can activate this flow using Deploy button. Then we can see that our serial port is connected and working properly. Next, we use our serial port to check a version of CANDUPTER. To do that, we need to first issue a V command over the serial port and then check a response. So next, we'll add a new node, and this time it will be a node type inject. We can edit it, use only message payload, and send just one string character V. Next, we'll add a flow connection, so our inject command will activate serial out port. This serial port will be also used to send other different commands. So let's give it a name, manual commands out. To verify our commands, we can use a debug node. We'll name it manual commands and connect to our flow. So this is a part where we send data and commands via serial port, and here will be a part where we receive and monitor data coming from serial port. We have here already a serial in node, and next we'll add here a debug node and name it monitor of serial input. Next, of course, we need to connect nodes, then deploy, then to test it, we'll switch the right panel to debug messages, and then click on inject V button. Now, in the debug window, we can see our command and response from CANDUPTER. Now we'll add a couple more commands. First will be a C command to close CANBUS channel. So here is inject node with string character C as message payload and connected to the same serial out and debugging nodes. Next, we'll add S5 command to prepare channel for 250 kilobit transmission. And next, we'll add O command to open a channel. Next, deploy. And now we can test it again. So here is C command. Next, S5 command. And next, O command. Now we can see that our channel was open and CANDUPTER is reading CANBUS messages and presents them on serial input port. Now, when we issue C command, channel will be closed. To better analyze our flow, we can clear messages and issue O command to open and C command to close again. That's how we start transmission manually, but we need it to start automatically when ctrlX starts. And that means we need to make an automatic sequence and issue first S5 command and then O command. So we'll make a new node type serial request and name it CAN serial request. Next, we'll add new inject node, issuing our first command S5, name it start auto, and then make sure that it will inject once after initial time. Next, to make our sequence, we'll add a JavaScript function and name it AutoStartCAN messaging. Then in our script, first we'll transfer S5 command, wait for request payload, and issue O command. Next, we'll add our connections. And finally, close a waiting loop. Please note the system is giving us a warning, linting error. When we click on additional info, system will tell us that loop is detected and we'll ignore it. Next, we'll clear messages and deploy. After deployment, system automatically starts, waits, and then opens a channel. For now, we can monitor changing variables only in the debug window. So, I'll add a new place where we can monitor them, a dashboard. First, I'll add a dashboard text node. We'll name it Full CANBUS Telegram, and for layout, we'll select value underneath the label. Next, we'll assign it to a new group, name it Full Telegram, and add a new default Home tab. Next, we'll close all three editor windows and then link our dashboard text node to serial port. Next, we'll empty the debug window and deploy. Now, when we go back to tab ctrlX Core, then Node Red, then Dashboard, we can see tab Home, Group Full Telegram, and item Full CANBUS Telegram updating. Back to our flow editor, and next we'll decode some of those BMS telegrams. So first, we'll add a new function and name it Decode BMS Telegrams. In the first step, we'll add two JavaScript MSG objects, one for dynamic decoding and one for results. Next, we'll parse message ID. And in our case, it will be 8 characters from message string, starting with character in position 1 and finishing with character in position 8. Please note that the slice method we used returns selected elements in an array as a new array. This method selects from given start up to, but not inclusive, given end. Next, we'll parse message length. And it is a character in position 9 and value 8. Next, we'll remove message ID and length from our message payload and leave only a string representing 8 bytes of message data. So next, let's look into our BMS message examples and check a message for product ID. So its priority reserve bit and data page equals hex 18, parameter group number PGN is equal hex FEEB, and sending device number in our case is 70 hex 46. So next we'll create a case statement and look for telegram with ID 18 FEEB 46. Next, we'll create a warning for our flow. This will help us find recording in the debugging window. And next, put our entire data string into result message using local variable product ID string. Then we'll close our case statement, and for now we are done with our function. Next, our connection. And next, we'll add new debug node called results to monitor data coming out of our function. Here we'll monitor message result. Next, connection and deploy. Now when we stop our channel and scroll to recorded messages, we can easily find our warning followed by message result ID string. We can compare the string with our message example and see that our function works properly. Next, we'll convert the string representing 8 bytes into actual bytes, and then convert those bytes into ASCII string representing product ID. So we'll edit our function again and add couple lines to our case where we parse every 2 elements from data string and convert them to integer, then convert the result to ASCII character, and then put them together into ASCII string. So let's test it. After channel close and scroll, we can see product ID and we are reading it properly. Next, we'll present this result in dashboard. So here's new dashboard text node. We will name it product ID and represent the message result prod ID. After deploy and after opening a dashboard, we can see product ID value showing for a very short time every couple seconds. So to fix this, we'll edit our function, add new global variable result ID and transfer into it our ASCII string, and then add the new message product ID, which will be updated by this global variable. Next, we'll change dashboard message call to our new message product ID. Now, after deploy, when we go to the dashboard, we can see product ID showing properly. Next message from BMS we'll decode is 1FFFD, and this message provides actual battery voltage and current. So, back in our function decode BMS telegrams, and here we'll add new case for ID 19FFFD46. First, we'll look into message data definitions, and battery voltage is represented by bytes 2 and 3 of our data. So, here is a code to extract the voltage. Here is byte 2, data string elements 4 and 5, and here is byte 3, data string elements 6 and 7. Next, we convert those 2 bytes into integer and divide by 20 since our precision is 0.05 volt. Please note that depending of the endianness of data sequence, you might have to change byte order in this formula. Next, we'll write similar code for actual battery current, and then add 2 messages working with global variables for dashboard. Next, we'll add 2 new dashboard nodes, one for actual battery voltage and one for actual current. And next, after deployment, when we go to the dashboard, we can see actual battery voltage and current. Back in our flow editor, what we did so far is only receiving and decoding CANBUS messages broadcasted by BMS system. Next, we'll try to send a message. We'll use a command 1FEA4 to switch off BMS main power contactor. But first, to be able to test our command, we'll create additional dashboard node showing battery operating status. So we'll open our function decode BMS telegrams. Add the case for ID 19FECA46. Monitor only first 4 bits from byte 0. Then, if their value equals 1, set text string power is off. And if their value equals 5, set text string power is on. Then we'll finish our function. Next, we'll add a dashboard node for this result and name it power status. After deploying, in dashboard, we can see new node showing power is on. Back in editor, we'll add new node. This time it will be a dashboard button named power off. This button, when clicked, will send a following payload message to our serial port. How did we create this message? Here is a definition of CAN adapter command to transmit 29-bit CAN frame, and here is a command for BMS. So, first part of our payload message is character X with identifier 19FEA446. Next is number 8 for number of data bytes. Then first data byte is 01 and it is a default battery ID. And the second data byte is 00 and it is a request to turn off main battery power switch. All remaining data bytes are not significant and will be set to 0. Please note that right now our system is supplied from battery, so when we switch off power contactor, we'll power down entire system together with CANBUS network. So let's test it. Here is our power off button, and when we click on it, first power status changes to power is off, and then our demo shuts down and we'll lose connection to it. We can see our command works properly, and next we'll supply our demo from outside source so we can add another button to switch battery contactor on. So we'll add second dashboard button. This one will be green and we'll be sending the same message but with second data byte equals 01. Now we can switch our battery contactor off and then on again. Next, we'll finish our project and add more information about our battery into dashboard. So we'll add new cases for temperature, state of charge, remaining discharge time, and remaining discharge capacity. Add matching dashboard gauge and text nodes. And here is our new dashboard. And here we can see how it will present itself on tablet or cell phone. Thank you for your attention.